know of peak and rule? So Daniel Kahneman and Amos Tversky are the sort of considered fathers of behavioral economics, and they basically looked at a lot of things behind the irrationality of human decision making that we have looked at earlier. We mentioned this earlier. And after that, in fact, Richard Taylor, who got the Nobel Prize this year, was a sort of a student of Kahneman and Tversky. And he too obviously did this Nobel Prize, this work. But anyway, Kahneman later on continued working after Tversky died, and he talked about this thing called peak end rule, which basically, when there is a long experience, people try to judge the experience not by the entire experience, but the peak at the end. And so, in fact, you can read this article. So he did this by sort of having different people take part in a reasonably hard surgery. And then the only difference between them was one subset of them basically at the end of the surgery sort of tapered off without too much pain. The other one, they sort of increased the pain a little bit. And then they asked after a while, about what they remember about the surgery. And the people who had a little extra pain at the end thought that was a really, really bad surgery. And the other people thought it was good. That's what I'm trying to do. So if you remember the class by Raspberry Bars, you remember three things, right? So that's really nice. But seriously, one of the things that I sent in mail, and I don't obviously want to go into the prime philosophy slides, but I do want people to understand that a mark of education is to essentially understand the irrationalities that you have and going over it. Okay? And so, if in fact peak and rule is something that you sort of do without thinking, try to make up for it. Try to realize that you are essentially judging something by the very end rather than the entire experience. And similarly, if you're judging something by a vivid single example rather than the big statistic, then you're again wrong. And so you need to train ourselves to be moved by the statistic. That's what Oscar Wilde says, that essentially to be able to see dry statistics and be moved by them. That's important because that's something that we didn't evolve to do, but we need to learn to do it. Otherwise, we will keep falling on the same sort of bogus conclusions that this I don't know. Again, this is from the upstairs. Anyway, so what I'm going to do today is Bayes network inference, and then next class, and maybe towards the end of today's class, and certainly next class, we'll talk about this network learning. I guess this is going to be very. Oh yeah, I have one more. Okay. So that's what we're going to do in today's class. So are there any questions on the things that we have discussed about Bayes networks or last class? Okay. So let me start by talking about okay. Can you guys hear me without this?
Yes.
Okay, then I'll just proceed. So let me start by talking about factorization of probability distributions, because we mentioned this quite a bit, right? That essentially what Bayes networks are doing is the topology is sort of factorizing a probability distribution. And the factors are sort of, you're multiplying small distributions such that you get a big distribution. That's the basic idea. Except the multiplication is a special type of multiplication. It's not matrix multiplication, neither is it simple integer multiplication. It's the closest is, those of you who have taken databases, it's closest to join operation. You join two relational tables and you multiply the corresponding numbers. That's what the multiplication is for the distributions. Now, I want to just make you understand that, because people keep talking about did it factorize well, or how does the distribution factorize, and how does and given a topology, what is you can think of the topology as a particular way of factorizing the distribution. Okay, so as an example, in this particular case, I have a very, very small network. Okay, there is A is causing so A basically is connected to B and C, and as far as the network is concerned, I can just give it by giving the distribution, prior distribution of A, prior distribution of B given A, and C given A. Right? So this is what you think of. Now, you can write these actual distributions as little tables, relational tables. That's what I will do. So I will actually write this in longhand. When I write this, this is basically in longhand, this particular longhand notation, right? So A 0.7 means A 0.7 and not A 0.3. Right? And similarly, this one is AB 0.3, A not B 0.7, not A B 0.8, not A not B 0.3. So I just wrote what is actually written here as a conditional distribution. I just wrote the conditional distribution in a sort of a tabular form. And similarly, I have a table here. And the argument is that this network essentially is giving the full distribution. Full distribution would be a table on 3 variables, A, B, C, right? And it will have 8 rows. A joint distribution is nothing but the truth table with the numbers corresponding to the likelihood that that particular kind of word will occur when you randomly look at the possibilities. Okay, and so the interesting thing is you can actually get that by this network is essentially just saying the formation of this network is essentially saying the PABC. This is the distribution. It's not just a single variable. It's the joint probability distribution of A, B, and C together, where A, B, C are all Boolean variables. Okay, it's nothing but, given this network, it can be written as a distribution of A times distribution of B given A times distribution of C given A. You can see this, right? This is basically the definition of the Bayes network. Because given this Bayes network, you know that you can compute the joint entry by in terms of starting from PA and then PB given A, PC given A. Right? You have done this. You have done this for individual entries. I'm just saying what you did for individual entries is really, actually you're doing it for tables. And if you do it for tables, you get the full distribution. Okay? And so now if I write this, then now let's see, P given A, and the P of A is this particular table here. So A is 0.7, not A is 0.3. And then B given A is this table. So I write that. AB is 0.3, A not B is 0.7, not AB is 0.8, not A not B is 0.2. Now I need to multiply this. Okay, when I multiply this, so here is the very interesting thing. The factors that you get, okay, let me actually continue this. So here, this little table corresponds to a conditional probability table. This little table is also corresponding to a conditional probability table. Okay, and if I multiply them, I get, what I'm going to do essentially is I'm going to join these tables. So when I join the tables, this row A.7 will join with everything which has A2. Okay, so you'll get A.7 will join with AB.3. Then I'll get AB, which is 0.7 times 0.3. Okay, so that's what I'm going to do. A.7 with AB.3 will become AB, this and this together, and with the number 0.7 times 0.3. Okay, and similarly, this will also join with A0B. So A0B, when it joins, it becomes 0.7 times 0.7. You see what I'm saying? So this is called a new factor. This is called a new factor. Okay, so you started with these two small factors and you got this intermediate factor. Now I'm going to multiply this intermediate factor with P of C given A. Okay, P of C given A is this number, this particular table. I do the exact same thing, join these two tables. Except this time when I join the two tables, I will get 8 rows. Not just 4 rows, I will get 8 rows. And it would look like that. Okay, I'll walk you through a couple of the rows. So consider this ABC. This AB can join with this AC. I will get ABC. But then I will have to multiply 0.7 times 0.3 times 0.45. So that's what I have here. And similarly, this AB can join with this this AB can join with A0C, because this table doesn't have B, obviously. Right? So A0C and AB will get AB0C. And AB0C will be 0.7 times 0.3 times 0.55. At this point, I have a much bigger factor. It turns out this big factor is nothing but the distribution. Do you see this? So this is what I had in the back of my mind when I said conditional independences are factorizing the distributions. So big table got multiplied into, got written as a product of 3 small tables, where the product happens to have this interesting semantics. It's basically a joint semantics. You get this now? Okay. So this is what I mean by saying distribution has been factorized. And one of the interesting questions, since we are here, one of the interesting questions is, in Bayes networks, the beginning factors are all actually factors that have probability semantics. They're all conditional probabilities. Right? For example, this little table here is probability of A given nothing. This little table here is probability of B given A. And this little table is probability of C given A. So these numbers actually have probability semantics. They are conditional probabilities. But what you get in the middle, the factors that you get in the middle, may or may not have any probabilistic semantics. But again, at the end, it will be joint distribution, so it will have probabilistic semantics. Do people get this? In the beginning, in Bayes networks, you have conditional probability tables, so they have probability semantics. In the end, if you multiply all the tables out in the way that is asked of you by the Bayes network, then you will get joint distribution that has to have probability semantics. In the middle, you can basically get these things. They are not actually probabilities necessarily. In Bayes networks, that's the case. And I remember I talked about Markov networks. In Markov networks, even in the beginning, these little tables in the Markov networks, they don't have probability semantics at all. They call them affinities. How much does A like B? If A is positive and B is positive, A is true, B is true, how much is the affinity for that configuration? You will give some number, 8. We say, what is this nonsense about 8? What is probabilities cannot have 8. Okay, that's completely fine. What happens is in the end, you will have a huge number of numbers multiplied. And you think, where is the probabilities here? Well, this is the joint distribution now. So assume that all of those should add up to 1, which means you divide each entry by the sum of all entries. Do you see what I'm saying? If I ever tell you, hey, I have a probability distribution 9, 7. That doesn't look like probability distribution, but it's like alpha times 9, 7 is what I have in mind. Where alpha equal to 1 by 9 plus 7. Then it will become a probability distribution. You see what I'm saying? And that particular, so in Bayes network, you don't need to actually do this additional last step, which is normalizing the joint table such that it becomes probabilities. In Markov networks, you actually have to do this last step so that it pick up joint distribution. So for those of you, if you actually ever go and read anything about Markov networks, they'll talk about the bad Boltzmann constant. Basically, this stuff that, giving something like 9 and 7, I have to convert this into probability by actually multiplying each entry by the inverse of the sum of all entries. Which, I just said this and I'll repeat it next class, that in some sense means the probability that you're going to put here is not just dependent on this parameter, but all the other parameters too. This is what's called parameter entanglement. Just a foreshadowing. You will start hearing about it a little later next class. One good thing about Bayes networks is there is no parameter entanglement in simple cases. Okay, but this is again a very interesting abstract point about what do the people mean by saying Bayes networks essentially factorize a distribution. This is what they're saying. And this also makes you realize, later on in today's class we'll point out that doing inference on these networks, essentially, if you're doing exact inference, there is a particular approach called variable elimination that I won't go into too much detail in this class because we don't have enough time. But the version before variable elimination I will mention, and then I'll say variable elimination is just the efficient version of the one that I'm telling you, and where you cache the intermediate results. And caching the intermediate results means remembering some of these intermediate factors somewhere in the memory, so that you don't have to recompute them again. Okay, sometimes you may wind up recomputing these factors many times, and that's just a waste of time, and that can improve your efficiency. That's what variable elimination does. Okay, but that's all in the background. So what I'm going to do in the next few minutes is talk about how would you go about manually constructing a Bayes network for which you have some expertise. You know what things are connected to what things, or at least you have an expert who will tell you what things are dependent on what things. And using those experts, you want to write a Bayes network and then assess the numbers by asking the experts. Okay, so in the beginning, that's how Bayes networks are used, and even now actually Bayes networks can be used in many situations by essentially asking experts to provide both the topology and the numbers. So there is this task called knowledge engineering task. What the knowledge engineering is, you would be a knowledge engineer. You would go and essentially you know enough about Bayes networks, but you don't know enough about medicine. So you go to a medical expert, and or in this particular case, in the example we'll be looking at, we'll be going to a Los Angeles earthquake burglary expert. Okay, and then you're going to ask, okay, I have this Bayes network technology, but I don't know how to write the network. So I'm going to ask you a bunch of questions, and you tell me answers to it, yes, no answers, hopefully. And after that, I'll ask you a bunch of number questions, and you'll give me numerals for that, and then we would have specified the network. This is how we think about it now. So this is basically, one half of using Bayes networks. The other is, if there are no experts, then you have to learn it from scratch. That would be talked about next class. Okay. So in the Barghouli-Fake, Mary calling, John calling, alarm going up, I basically imagine that I know the variables, so I'm just going to start putting the variables in the network one by one by one, in some order. Okay? Imagine I decided to put Mary calls first in the network. Clearly that's the only node in the current network, so there are no edges to begin. Then suppose I put John calls. So I, the knowledge engineer. Then I ask you, the Los Angeles Barghouli experts, given your understanding of the problem, do you think John calling is independent of Mary calling? Do you think John calling is independent of Mary calling? That's all I'm asking. Do you? If you think it is independent, I won't put any link. I'll just leave them alone. But if you think they are not independent, then you should tell me, no, they are not independent. Then I'll put a link. Okay. In the problem that we discussed, is John calling independent of Mary calling? How many people think it is independent? Okay. How many people think it is dependent? Okay. Why do you think it is dependent?
Because it's their parents.
No, don't think about that tree. Think about the semantics of the problem, the English description of the problem.
So one is calling in the same problem they're calling about John.
Do you guys get what he's saying? Okay? There is a good reason to believe that if Mary is calling, then John is probably likely to call too, for about the same reason, that there is a Barghouli accurate. So in fact, John calling is dependent, it's correlated with Mary calling. I'm not asking, is Mary calling causing John calling? No, I'm only asking, if I told you just now Mary called, is your belief that John will be calling, is it going to change or not? If it's going to change, then they're dependent. If not, they're independent. Yes?
I was just going to ask you if there being a correlation to the same with dependency.
Correlation is exactly the dependency. Probabilistic dependency is correlation. And I sent this whole long mail as well as talked about causality last class. Causality is not something that we can capture right away. You need to know causality of the domain yourself. The Bayes networks just basically are capturing the correlation. Probabilities capture correlation. Machine learning learns correlations. This is the problem. And we repeatedly confuse causation and correlation. Freshly, every day, morning. Okay? And that's why we are a sort of a bozo race. Called a human race. That's why we should be careful. Anyway, so John calling is in fact dependent on Mary calling, because of which you will put a link. Suppose you don't know enough about the domain. You're not, in this case, obviously, this guy is an expert, he understands how Los Angeles works, right? But suppose you don't know enough about the domain. You're not sure whether it's dependent or not. What would you rather err on the side of? What? Put a link. If you put a link, nobody can sue you later on. Okay? Do you understand what I'm saying? Okay. So, now again I decide, suppose I put alarm now. Next. Okay. Then I put the alarm in and I ask the same question again. Is Mary calling dependent? Is alarm correlated with Mary calling? Is alarm correlated with Mary calling? Yes. Why should put a link there? Is alarm correlated with John calling? Should put a link there too. I can't ask any more links because those are the only two guys before me. Right? And notice that the fact that this is acyclic and directed acyclic helps, because only as the network is being incrementally constructed, you only ask, are the guys already in the network correlated with me? You're not going to ask yet about the future, because the future guys will be handled separately when they come in. Right? Then I put, let's say, burglary. Okay? Now I ask the question, is alarm correlated with burglary? Okay? Is Mary calling correlated with burglary? Is Mary calling correlated with burglary? I mean, the question is, now that you put this link, then you have to ask, is Mary calling correlated with burglary, and the correlation can't be explained just by alarm going off.
If alarm doesn't go off.
So it could be that Mary is like sort of a closet burglar. Then you need to take that into account and start putting extra links. But to the extent you believe that that's not the case, you won't put a link. You see what I'm saying? And similarly, you didn't put a link from John calling to burglary because you believe this is the semantics of it. Now, who is to say what is the semantics? You, the expert. Okay. Now, earthquake, same way. Okay. Now, earthquake is occurring. Is alarm correlated with earthquake? Okay. I'll put that. Now, is earthquake correlated with burglary? Is earthquake correlated with burglary? Yes. Then that was the whole explaining away. Right? Remember, correlation doesn't mean only positive correlation. Correlation means correlation. It can be negative or positive. If I tell you burglary occurred and alarm is going off, your belief in earthquake will change. So in fact, burglary is correlated with earthquake. You see what I'm saying? So I throw that link too. Okay? So that's it. Now, of course, I also have to ask, is earthquake correlated more with Mary calls in addition to these numbers, these links? And if you think Mary is like a closet burglar, you have to still put that link. If not, you don't. This idea of probabilistic influence being mediated by intermediate nodes becomes a very important thing. In fact, in the next slide or so, I'll tell you that sometimes you will invent non-existent intermediate nodes just so that you can put fewer links. Strange stuff. Yes?
Oh, I know it's a stupid question anymore, but should it be like the arrow the other way?
Which arrow?
The burglar.
No, you'll always put the arrow to the guy who came later. This
So
is the idea.
burglary implies.
So,
or
no. This is not implies. The arrows, in fact, the next slide will tell you that. The arrow doesn't at all say implies. It doesn't say causes. It just says probabilities are correlated. The more you really understand that, the smarter you are compared to like a huge amount of population in the world. Okay. So basically, and again, as to why this way, this basically is giving you a nice procedure. You will only ask whether I should put an arrow from a past variable to the current variable. There is an order. The variables are coming in order into the network. Now notice, I got this network. Right? If I had asked, instead, if I put things in the order of burglary, earthquake, alarm, John calls, Mary calls, I would have gotten that network. Did you see what I'm saying? If you ask the questions in that order, if you started by making this network such that I first put burglary, of course there is no link there. Then I put earthquake. Nothing yet happened. I just put burglary and then I put earthquake. Is burglary going to be dependent on correlated with earthquake? The semantics are no, because they can be happening independently. Because I haven't yet started thinking about alarm. Then when the alarm comes, then I say, yeah, both of them can be actually correlated with alarm, so I put links from there. And then when John calls, then I realize that John calling is connected with alarm calls, and I don't need to have any special extra thing from burglary and robbery. And then the same way from alarm calls to Mary calls. Just by changing the order in which you put the variables into the network, you reduce the number of leaks. But you have to understand that to be able to do this, you need to know the causal order. This is the true causal order. So you can't very well say that network is causal, this network is causal. You realize that both of these are base networks for this domain. Okay? And obviously you can't have causes in both ways. So this is why arrows are not causes. And it's very important for you to understand. And in fact, in the little project that you have due, end of, by next Wednesday, I will force you to write one network like this, and from this come and basically give the numbers, let's say, for this. So in fact, actually I'll ask this question. If I gave you this network right now, okay, and I said this is actually the joint distribution, except that's a ground truth, okay? Now it turns out that you made this network for the same domain because you asked the questions in the wrong order. You put the variables in the wrong order. Can you specify the probabilities for this network, given that you know the full joint distribution? Yes, because you know that I need, at many calls I need prior probability of many calling, which is marginalize everything. So since I have the full joint distribution here, I just have to compute probability of many calling given that entire joint distribution and put that number there. And secondly, for John calls, this one will need probability of many calls. I can get this from here. And this one will need probability of John calling given Mary, probability of John calling given not Mary. I can get this from here too. If this is the ground truth, I can get these numbers. The strange thing now is the same big table at the end, the 32-row table, has been factorized in two different ways. Have you ever thought of factorizing a single number in two different ways? That's what you did here. You factorize the network in two different ways. This is a better factorization according to many of you because it requires fewer numbers to have been given by the expert. If you factorize it this way, you will ask the expert for a lot more numbers. Of course, if I told you this is the ground truth, then obviously you can compute it. Okay, now lots of questions. Yes.
So, what is the point then? If one we came up with is dependent on having what looks to me like the exact same amount of information, like what did we gain by it?
There's nothing. So the point is, so here is the thing. So imagine you came up with that. You would have needed what? What did we find? You would have needed 10 for probabilities for the top one. To specify the top one, you would have needed 10 numbers. To specify this, how many numbers would you need? You can count and actually convince yourself that with 13. Because 1 here, 2 here, 2 plus 1.